Let's do an exercise on this. Assume that the rotor of a helicopter turns at an angular speed of 3.20 revolutions per minute, RPM, revolutions per minute. Express this angular speed in radians per second, and then, if the rotor has a radius of 2 meters, what arc length does the tip of the blade trace out in 3 seconds? So in order to go from revolutions per minute to radians per second, we know that, so we can come here and say that omega is 3.20 revolutions divided by a minute. Then we know that 1 revolution is 2 pi radians, so we do this conversion factor. So 1 revolution is 2 pi radians, and we know that 1 minute is 60 seconds. So here we have 3.20 multiplied by 2 pi and divided by 60, and the units that we have here, we have that revolutions go with revolutions, minutes go with minutes, and I only have radians divided by seconds, which are the units I'm looking for. So this is going to be radians divided by the second. 0.33 radians per second. So that's omega in the SI units, which is radians per second. Now we want to calculate, so we have the blade of the helicopter, and at the tip, knowing that this is 2 meters, it's going to be moving for an time interval of 3 seconds, and we want to calculate the delta omega. Well, we know that delta omega is going to be omega t, as they tell us angular velocity is constant. So what we have here, well, this is delta t, so it's just 0.33 times 3 seconds, and this is about 1 radian, sorry. It's 1 radian, the angular displacement of the tip of the blade. That is 1 radian, which is the angular distance traveled by the whole blade. If we're interested in the tip of the blade, then what we do is we use this expression, delta S is R times delta theta, and that's 1 multiplied by 2 meters, so it's 2 meters. So 2 meters is this distance. This part of the blade will have traveled this smaller distance, but all the different points of the blade will have traveled 1 radian. So the angular displacement is the same one, even though the linear displacement is not. Now, what happens when suddenly the wind starts to blow and the blades of a wind turbine begin to rotate from rest? Well, we have acceleration there. And just as the change in speed leads to the concept of linear acceleration, a change in angular speed leads to the concept of angular acceleration. An object's average angular acceleration during a time interval delta t is the change of its angular speed divided by delta t. So that's for the instantaneous angular acceleration. Remember the sign criteria in rotational motion. Positive is going to be counterclockwise, so we can have positive and negative, or negative angular velocity and positive and negative angular acceleration. So, for example, if an object is moving counterclockwise, we know that omega is going to be positive, but we can have that the magnitude of this angular velocity is decreasing, so we are going to have a negative acceleration. If omega final is smaller than omega initial in magnitude, then we're going to have that the angular acceleration could be negative. So be careful with this, the sign criteria when you're working with angular motion. Let's solve this problem with angular acceleration. An airplane propeller slows from an initial angular speed of 12.4 revolutions per second to a final speed of 5.0 revolutions per second. During this process, the propeller rotates through 21.0 revolutions. find the angular acceleration of the propeller in radians per second square, assuming it is constant. The data that we have are omega 0 is equal to 12.4 revolutions per second, and the first thing we need to do is to change from revolutions per second into radians per second, which then we multiply by 2 pi radians and divide by 1 revolution, and we get 77.9 radians per second. That's the initial angular velocity. The final angular velocity is 5.0 revolutions per second. We do exactly the same. And that's the final angular velocity in SI units. They tell us that alpha is constant and delta theta is 21 revolutions. We do the same, we go from revolutions to radians, and we'll get 131.9 radians. So now what we want to calculate is the angular acceleration. We use the equations of kinematics for this particular case of angular motion. Just as we had seen in linear motion, 2 times the acceleration times the displacement, in this case the angular displacement, is equal to the final velocity squared, in this case the angular final velocity squared minus the initial velocity squared. We can use this, we know final velocity, initial velocity, we know delta theta, and then we just calculate alpha. And we get that the acceleration is minus 19.3 radians per second square, and it's negative because it's going from a higher angular velocity to a final, smaller angular velocity.